All right, so we are in part 1 of 9.3. So we have, even though we're only in the third section of the chapter, we have actually we've covered quite a bit of ground. So I want to just kind of recap some of the things that we've talked about, because we've talked about a lot of little details that we've kind of put together. So we started talking about sequences, and we defined a sequence as something that a function whose domain is the positive integers. We have this list of numbers that we can think of as a function of positive integers. For a sequence, if the nth term approaches a limit, then the sequence converges. That's all we need to worry about for a sequence is, does the nth term approach a limit? And one of the tools we used for sequences was we associated the terms of a sequence with a function. If we plug in a positive integer for the function and it's the same as the terms of the sequence, then we can use our rules for finding limits of functions to find limits of sequences. So we can determine if a sequence converges that way. We also talked about the squeeze theorem. If we can squeeze the terms of a sequence between the terms of two sequences that we know converge, then we know that our sequence converges. Then we talked a little bit about bounded and monotonic sequences, and that was really the kind of the basis for all of it. Is that the sequence is bounded and monotonic, so it doesn't get bigger than something, doesn't get smaller than something, and they're always increasing, or staying constant, or always decreasing, staying constant. Then that sequence is going to converge. So then we related a sequence to a series. If we sum the terms of a sequence, then we get what we call a series. And we wanted to know if the series had a sum, if the sum of the series approaches some limit. And we said that the basic idea there was if the sequence of partial sums for our series converge, then we say that the series converges, and the sum is that limit of the sequence of partial sums. And then really the rest of the chapter is different shortcuts rather than trying to find the sum of the sequence of the limit of the sequence of partial sums. We find these shortcuts that allow us to do the same thing, just in a different way. So a couple of types of series that we've talked about so far. Geometric are nice. We have a nice formula for the sum. We can figure out quickly and easily if they converge. So geometric series are our friends. We use them for lots of things. We talked about a telescoping series. Use partial fractions and try to cancel out terms to find the sum of a telescoping series. We talked about the nth term test for divergence. If the nth term does not approach 0 of a infinite series, then the series does not converge. And then we said the contrapositive was true. If the series converges, then the nth term approaches 0. I mentioned briefly some difference in product rules for series. If we have series that we're trying to combine, we can add limits, we can subtract limits, and we can multiply limits by a constant. Different rules for series. And we said that if we delete a finite number of terms from the beginning of a series, it doesn't affect the convergence or divergence. That's a lot of little details that we've talked about so far. Just wanted to kind of refresh us before we started today. So what we're going to talk about today is just one particular test, the integral test. So we'll state the integral test. I'll outline how the proof works. We're not going to go through the proof. And then we'll talk about it a little bit. So we have a function. And we have several conditions on this function. If f is positive, continuous, and decreasing. That third one is the one that people usually kind of forget about. For x greater than or equal to 1, so we're talking, we said our series, our sequence was defined for positive integers, so we're usually talking about the positive integers. And we can relate our terms and this tells us if a sub n equals f sub n, or a sub n equals f of n, that tells us that our terms are positive. Then our series for n equals 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx either both converge or diverge. So what we're doing here is we're relating the terms of our sequence to a function. We want our function to be positive, continuous, and decreasing. Then we can evaluate this improper integral. If the improper integral converges, then our series is going to converge. If the improper integral diverges, then our series is going to diverge. And if we draw visually what the proof looks like, I'm just going to draw a picture here and talk about it for a second. So here's my positive decreasing function. And I'm going to put my 1, 2, 3, 4, etc. What we do for the idea of the proof is we look at the area of the inscribed rectangles and the area of the circumscribed rectangles. And we form these rectangles for the entire series, for the entire function. The sum of this series is going to be greater than or equal to the inscribed rectangles and less than or equal to the circumscribed rectangles. The value of the integral puts an upper bound on the area of the inscribed rectangles and a lower bound on the area of the circumscribed rectangles. So the integral serves as a bound for the terms of our sequence. So the series, because this is constantly decreasing, the series would be bounded and monotonic. So if the integral converges, then the series is going to converge. If the integral diverges, then the series diverges. So if the integral diverges, that means that our areas are unbounded. So it would not be bounded. So that's the outline of the proof of the integral test. So questions on what the integral test is telling us. This one's a nice one to apply if we have a function that's kind of well behaved and that we can evaluate the integral easily. Sometimes we might think we could apply the integral test where we want to apply the integral test, but that integral is very difficult to evaluate. So let me look at a couple of examples. And then we will be done. That's really all I wanted to talk about today, was to talk about the integral test. So let's look at an example. So we have the sum n equals 1 to infinity of 1 over 3n plus 5. So when we want to apply the integral test, we want to make sure that our function satisfies the conditions. So if we're going to relate this to a function, f of x equals 2 over 3x plus 5, we're relating this to this function. Is this function positive for n greater than or equal to 1? We're not plugging in a negative number, so it's positive. So we can say a sub n greater than 0 for n greater than or equal to 1. This is a continuous function. We don't have any discontinuities because we're saying x is greater than or equal to 1 or n is greater than or equal to 1. How do we make sure that this is a decreasing function? That's the third condition of the integral test, is we need to make sure this is decreasing. What would we do to make sure this is a decreasing function? Okay, so we can make some kind of argument that as x gets larger, this denominator is getting larger. So for each successive x, we're dividing by a larger number. So each term would get smaller. We can make an argument like that. What if we had some function where that isn't as clear? What other analytic tool could we use to ensure that our function is decreasing? We could look at a limit.
Usually it was 1 and x is 1 and x equals 8.
Okay, so let's expand on that idea a little more. Josh says something about the first term and a very large term, and look at the kind of the average slope between them. Let's make that a little stricter. Derivative. We can take the derivative. If the derivative is what guarantees us that this would be a decreasing function? If the derivative is negative. So if we take the derivative and if it's negative for n greater than or equal to 1, then we're ensured that this function is decreasing. So for this particular function, you can make some kind of argument that x gets larger and larger, so this fraction gets smaller and smaller. That would be fine. Sometimes it's not clear, it's not entirely clear from looking at the function that that's the case. So the way to make sure is we look at the derivative. So I'm just going to go through that f prime, and I'm going to say this is negative 2 times 3x plus 5 to the negative 2 times 3. Because this is 3x plus 5 to the negative 1, right? Oh, this should be a negative 1 then, right? Negative 1. I just need a negative. So this is just minus 3 over 3x plus 5 squared. Is this negative for x greater than or equal to 1? Yes. So this is less than 0 for x greater than or equal to 1. So that ensures us that this function is decreasing. So if it's not clear, if you can't make some kind of direct argument that each term is getting smaller and smaller, you're not 100% sure, take the derivative. We need the derivative to be negative. So we can apply the integral test. We need to ensure that all the conditions apply before we use the integral test. So I'm going to say integral test applies. We've satisfied all the conditions. We've made a good argument that all the conditions hold. So we're going to look at the integral from 1 to infinity of 2 over 3x plus 5 dx. Do we remember how to do these improper integrals properly? Right, we define a dummy variable. Yes, did I make a mistake?
What happens to the 2?
Oh, did we?
It should be negative.
It should be -2. That's where my 2 came from. I had a 2 in the numerator. So this should be -6. Thank you. Doesn't affect the sign, but it affects the magnitude. I was looking at the exponent and I thought I messed up the exponent and I forgot that. All right, so Robert says we define a dummy variable. So we rewrite this as a limit. This is the limit, and I usually use b, the integral from 1 to b of 2 over 3x plus 5 dx. And we're going to evaluate this integral. So what does this integral evaluate to? Two-thirds. So I'm going to write the limit as b approaches infinity of 2/3 natural log of 3x plus 5, and we're evaluating that on 1 to b. And we don't technically need the absolute value because x is greater than 1. So we always get a positive number in there. So this equals 2/3 the limit. I'm just writing this out. B approaches infinity of the natural log of 3b plus 5 minus the natural log of 8. And this limit is what? As b approaches infinity, the natural log of 3b plus 5. Right? Natural log of a very large number is another very large number. Equals infinity. So this diverges. I'll say diverges. So the series diverges. So because this integral diverges, this improper integral diverges, my series diverges. All right, I want to look at one more example and talk about one other thing that we have to be careful with. Any other questions on this example? So we need to, couple of things with the integral test. We need to ensure that our terms are positive, that our function is decreasing for our interval, and that we're talking about a continuous function. All right, let's look at another example. Often the difficult thing with the integral test is evaluating the integral. Sum n equals 1 to infinity, n over n to the 4th plus 1. So we're going to say f of x, we're going to relate this to a function. F of x equals x over x to the 4th plus 1. Is this positive for x greater than or equal to 1? X to the 4th is always positive, x greater than or equal to 1. So this is greater than 0. And is this continuous? Do we have any discontinuities for x greater than or equal to 1? No. X, so their function is greater than 0 and continuous. For x greater than or equal to 1. We can make an argument that as x gets large, the denominator gets large faster than the numerator. So this is going to be decreasing. If we want to make a stronger argument, we would look at the derivative. So if I take the derivative, f prime, it's relatively clear here, but if it weren't clear, we can take the derivative. X prime, or f prime, we're going to use the the quotient rule. So I get x to the fourth plus 1 minus x times 4x to the third all over x to the fourth plus 1 squared. I'm going to rewrite this. It's not clear that this is negative, so I'm going to rewrite this as x to the fourth minus 4x to the fourth plus 1 all over this denominator, x to the fourth plus 1 squared. And we get minus 3x to the fourth plus 1 over x to the fourth plus 1 squared. Is this negative for x greater than or equal to 1? Yes. So this is less than or equal to less than 0. So our integral test applies. Our function is decreasing, it's greater than 0, it's positive, and it's continuous. Well, now we need to evaluate this integral. So we're looking at the limit as b approaches infinity of 1 to b of x over x to the fourth plus 1 dx. What are we going to do with this integral? Usually do partial fractions when the degree of the denominator is larger than the numerator. So we could do partial fractions. That would work. Is there an easier way? Anybody see an easier way? I'm going to say u equals x squared. du is 2x dx. So we have and I'm just going to rewrite the integral, just the substituted integral without our limits. We have 1/2 the integral of du over u squared plus 1. The integral of du over u squared plus 1, anybody remember? This one comes up a lot. Has to do with a tangent. Inverse tangent. So this is an inverse tangent integral. You would get the same place. You could do partial fractions. I think partial fractions would be a little uglier because you have this x to the fourth. All right, so we're looking at the limit as b approaches infinity of the integral from 1 to b of x over x squared, or x to the fourth plus 1, dx equals the limit from what we just talked about, b approaches infinity, of 1/2 the inverse tangent of x squared evaluated on 1 to b. If I write that out, I get the 1/2, the limit as b approaches infinity of inverse tangent of b minus the inverse tangent of 1 equals 1/2 as b approaches infinity. The inverse tangent approaches what? Inverse tangent is an angle. So what angle gives me a tangent of infinity? Someone said it? Pi over 2. What angle gives me a tangent of 1? Sine and cosine are the same? Pi over 4, there we go. So this is this less than infinity? So that's less than infinity, so the series diverges. Now this sum is pi over 8. Or the integral of values to pi over 8. That does not mean that the series converges to pi over 8. Doesn't mean the sum of the series is pi over 8. It just tells us that the series does converge. So it's easy to make that mistake. Oh, the integral evaluates to this number. That means the sum of the series is that number. All this tells us is that our series converges. So because this integral is finite, because this improper integral converges, our series also converges. Questions on the integral test? Do you guys like the integral test? No. When you can use it, it's kind of nice. A lot of times there are other arguments that are a little slicker, a little quicker to argue for convergence. All right, homework. There you go.